It's time to introduce one last type of transformation that we haven't seen before, just because the format of the things that we've done up to this point, they just didn't have this thing in it. And so what I'm talking about specifically is this number, a coefficient of x inside the operation. We've talked about a coefficient out there. That's different. I'm talking about a coefficient, in this case, inside the radical, or if we had something like this. We didn't have that before. If we had those numbers, they just would have been written in a different format. So we haven't seen this before, coefficient inside the radical or inside the operation that we're doing. So we want to see what that does to the graph. And basically it does two things to the graph. First, we're still going to set this whole term equal to 0 to find the horizontal shift. That'll still be the starting point of the graph. But one thing's going to look a little different here. You know, we got used to, like, if we saw x minus 3 squared, we would say, okay, x equals 3. And we talked about, hey, let's get in the habit of actually setting this equal to 0 and solving. Because I think I sort of told you ambiguously that that would be useful later. Well, now's the time, because now we have these coefficients. And so we can see, well, we've got a really clear result here that x, the horizontal shift here, x equals 1/2, it's not just the opposite of this number. It's a totally different number. And so why is this the case? Well, because when we plug in x equals 1/2, that's what makes this equal 0. That's where we're taking the square root of 0, and that's what the starting point is going to be. So it's no longer going to necessarily be just sort of the opposite of the number that you see here. So I'm going to put this starting point on the graph, x equals 1/2, along with our vertical shift of plus 3. So I'll put this as our starting point, x equals 1/2, y equals 3. Okay, the second thing that's going to happen because of this number is that, and by the way, we're going to call this m for now. So we could write this format as y equals a root mx minus h plus k. This is not a slope. I'm just sort of picking a letter to use there. What's going to happen is that this number is going to make the graph m times narrower. So this graph is going to be twice as narrow as a graph that was just root x. Okay, why is that? Well, let's just put in a number here, and I'm going to do a separate example just to kind of eliminate the complication of that -1 for a second. So let's just compare y equals root x and y equals root 2x. And I'm just going to say, all right, well, if x equals 10, and I just want to get a few numbers out here that we can talk about. So this would be root 10. This would be root 20. And if x is 20, I'm just going to put this one here. So let's compare these two for a minute. And by the way, both of these start at 0, right? When x is 0, y is 0. Okay. So I'll go through this a couple times because this is a really key part. I want to make sure that we get it. The change that we have to go from x equals 0 to x equals 20 in this graph to see this amount of change. To go up by root 20, we have to go all the way from x equals 0 to x equals 20. But in this graph, to get that same amount of change from 0 to root 20, we only have to go from 0 to 10. That same amount of change happens twice as quickly in this graph. This should make sense. You can think of it that, like, by the time we get to x equals 10, it's already acting like we're at x equals 20. We get the same amount of change in only half the space. And that's what we really want to think of this as. We get the same amount of change in half the space. So if I draw this here, let's say I sketch, now I'm going to start with as if this were just root x. Let's say it looks like that. Okay. Well, now we're going to get that same amount of change in only half the space. So we're only going to have to go this far over before we've gotten that same amount of change. And so the graph's going to be steeper. I know that doesn't look a lot steeper, but it is steeper. It's definitely steeper because we're starting at the same place and reaching a higher point. So it's definitely steeper. And I could exaggerate it more if we wanted. Just for visual, it might almost look like that. Okay, so I'll leave that one there for now. So what's happening is that we're getting the same amount of change in half the space. That makes the graph narrower. Now, it's going to look steeper, right? What we want to understand is that steeper isn't really what's happening. Steeper is in the realm of a number that goes here. Okay, why does that matter? Because this line is steeper. Why does that matter? Well, just like I told you, well, there's some stuff coming down the road where we want to get in the habit of setting this equal to 0, not just looking at the opposite of that number. I can also tell you now there's some stuff coming down the road where we want to get in the habit of seeing that this number will make a graph wider or narrower, and this number would make a graph steeper or shallower. They really are two different things, even though sometimes they look the same. So ultimately, we would end up with something like this one as the graph of this radical function. So it starts up 3, it starts over a half because we set this equal to 0, and then it's twice as steep as a normal radical graph would be. And of course, we could plug in some other point for x and find kind of a guiding point, to go through and graph it like that. But if we're just sketching it, it's going to be twice as steep as a normal root x graph. And one last thing that I want to do now that we've got all of these different transformations is, oops, pardon me, there we go. Now that we've got all these different transformations, and I may have just switched letters here, I forget, but same idea, is I want to give you one little pattern that might help you to remember them. So if we look at these two that are outside of the operation, right? They're not in the radical, they're totally outside the radical. And I'll type this here. Things outside the radical affect y, so they affect the graph vertically, the way that it looks. What do I mean by the way that it looks? Well, if k is positive, it looks like the graph should go up, and it does. If a is positive, it looks like the graph should be steeper, and it is. It's the way it looks. Conversely, and I'll point to these to be really specific, things inside the radical, or if we were inside something being squared, inside the operation. But to be consistent, I'll just write inside the radical here. So things inside the radical affect x opposite of how it looks. And what I mean by that is if we have, let's say, well, look at the example that we just had. We had root 2x minus 1. You see minus 1. You say, oh, minus is to the left. Nope, it's to the right. You see 2x. Oh, that should be twice as wide as if it was just x. Nope, it's narrower, not wider. So this is actually a pretty good general way to remember these, that things outside the radical affect y the way that it looks. Things inside the radical affect x, the opposite of how it looks. It's one way that you can kind of help keep all these transformations straight in your mind.